Hi, everybody. So I'm going to go over the, I don't know where I did. So I'm going to go over the homework 6, chapter 7. Those of you who are here, we're recording. So, and then I'll post this to YouTube like normal. So in this first question, we have a 1,000-kilogram car pushing a 3,000-kilogram truck, and they push with a force of 6,500 newtons. Rolling friction can be ignored. However, it's a little bit weird is we need to figure out what the force the car exerts on the truck is. So that's actually harder than you might think. We have our car and we have our truck, and they're assumed to be touching each other. So when we do our free body diagrams, remember that we do weight, normal, tension, forces. This is our car, and our car has a normal force and mass of the car G. And then there's a force that is on the ground, which they told us was 65, car on ground was 6,500 newtons. And there is actually a normal force pushing on the car due to the truck, which I'm going to call normal force on the car. And then we can plot this as this. For the truck has its own normal force and mtg. And then we have the normal force of the car due to the truck and the normal force on the truck due to the car. And this is y-x. And so this whole chapter is about interacting objects or systems with multiple masses. We don't need to worry about the y in this case. So we're just going to write mass of the car, ax, is F minus the normal force of the car due to the truck. Over here we have mass of the truck, ax is normal force of truck on the car. So what we're going to need to do is we need to be able to find the normal force of the car on the truck. That's what they're asking us for. It says, what is the magnitude of the force the car exerts on the truck? But from Newton's third law, we know that these two things are equal. So if we can find ax, we can determine what the normal force is. We just need to multiply by this because this is actually equal to what we want. Now, how we find this is noting those two things. If we add these two equations together, we get the mass of the car plus the mass of the truck is our ax equal to F minus nc over t plus nt over c, but these two things are a third law pair, which means they cancel. So we're trying to find ax so that we can put it in here and get what we want. Now, ax is the force over the mass of the car plus the mass of the truck. And I was told yours might be different, 1,000 and 3,000. So this is 1,000, this is 3,000. I'll write this up here. 1,000 kilograms and 3,000. So this is going to be 6,500 over 4,000. And that is 6,500 divided by 4,000, 1.625 meters per second squared. The normal force of the car acting on the truck is this times the mass of the truck. So this is 3,000 times 1.625, which is 4,900, 4,880 if you want to not round. So that's our 4,900, which is the answer. You could actually use 4,880. I think it would take it. But we found the normal force of the car acting on the truck. And it's actually a harder problem than maybe you think. But it's kind of a nice problem. Now, if you want to pause it here, this is just the force at the wheels. This is the force of the car on the truck. This is the force of the truck on the car that I called normal forces. Called them that because I assumed they were touching. This is how they did it, same way I did it. Now, what is the magnitude of the force of the truck exerting on the car? Well, we know it's a third law pair. So the answer to part B is simply 4,900. It's the same exact normal force that the truck exerts on the car. They are a third law pair. So hopefully that makes sense. It's actually not bad of a problem, but all of these problems we do the same way. We draw free body diagrams and then we link them by the ropes or the tensions or something else. So in this one, we have a dog that's pulling two sleds, one that weighs 100 kilograms, sled A, and one that weighs 80. And these two ropes actually are going to have different tensions. We need to be careful there. We also have friction. So we're going to need to figure out what tension 2 is. So let's take a look at what's going on here. We have sled A and we have sled B. Sled A has a normal force A, which will be MAG. Sled B has a normal force B, which will be MBG. And those in my problem were 180. Then there's a rope that goes from A to B. So I'm going to call that tension 1. It's rope 1. And then there's a rope that goes to the dog. But I'm not going to worry about the sled dog. I don't need to worry about the sled dog, as you'll see. The other thing that we have here is we were told there is friction. And this kinetic friction, we're assuming that this is pulling. In your book, it says that that's negative mu Kn. Well, the negative sign means it's opposite the direction of travel. So we're assuming that they're going to the right, and therefore I'm going to have a friction force here, which is mu K and A, and I'm going to have a friction force here, which is mu K and B. And I was told that mu K was 0.1. So mu K in this problem is 0.1. Now I need to write my equations. Normally, the only reason why we really need to know the normal forces is if we have friction, because it can't leave the snow. This tells me that Na is simply MAG. Move that over. This was MA. MBAY is similarly MB minus MBG, MB, NB minus MBG. And so NB is MBG. And that means that this is mu K MBG, this is mu K and MAG. Now, these ones, MAX is equal to T1, sorry, I should not ever forget to do this, and please don't forget yourself, Y and X. So T1 is positive minus mu K MAG. And then MBAX is T2 minus T1 minus mu K MBG. If I add these equations together, what I get is MA plus MB AX. Now the T1 goes away, but that's actually going to be what I want. But for now, I might need, well, let's look at the problem again. MAG plus MBG. I get combine these two. Now, the dog A and B, coefficient of friction, tension in rope 1 is 210. So I need to find A. because what I need to figure out is what is T1. I can find A, and then I can use either one of these equations to find T1. In fact, I'm going to use this equation to find T1. But I'm going to use this to find A first. So A of X will equal T2 minus mu K MA plus MB G. And then divide that whole thing over MA plus MB. And if I want to put numbers in here, let's go to this. AX is T2 minus mu K MAG plus MBG all over MA plus MB. Now T2, they told me, yours is probably different, was 200. I'm sorry, they want us to find tension in rope 2. So let's use this to find T1 and then we'll plug it in there. Sorry, you guys, being dumb. So looking at our equations again, please. MAAX was T1 minus mu K MAG. And MBAX was T2 minus T1 minus mu K MBG. MA and MB and mu K was 0.1. 180. All right, so they told me that T1 was 210 newtons. And they want to know what is T2. So from this, in order to find T2, I need to know AX, T2, T1. I know all this, I don't know AX. However, I can get AX from here. So if I divide both sides by MA, what I get is that AX is T1 over MA minus mu KG. Those M cancel. On that part, those cancel. This is 210 over 100 minus 0.1 times 9.8, which is 210 divided by 100 minus 0.1 times 9.8, and I get 1.12 meters per second squared. Now, in order to find T2, I need to use this one. T2 is MB AX plus T1, add it to both sides, plus mu K MBG, which is 80 times 1.12 plus 210 plus 0.1 times 80 times 9.8. And that is 80 times 1.12 plus 210 plus 0.1 times 9.8 times 80. And I get 378 newtons, 380 newtons, 380 newtons. Okay. So in this problem is about drawing the free body diagram correctly. Each of these has a normal force. Each of them has a weight. There's a tension 1 from A to B, and there's a tension 1 from B to A. There's a tension 2 from B to the dog, but there's also friction on both of these. Friction on A goes to the left, friction on B goes to the left. And that's how we got these diagrams. Then we write Newton's equations. The Y side can't leave the snow. So we get that the normal force is mg for each one of them. And then the X equations are MAAX, T1 minus mu K, MAG, because NA is MAG. And I chose X to go that way. MBAX is T2 minus T1 minus mu K NB. And from there, it's just a matter of solving for AX and then solving for T2. All right. It's not too bad of a problem. All right. Now these two blocks are connected over a massless rope that goes over a pulley. One of the pulleys, or one of the blocks, has a mass of 1.5 and accelerates downward at 3/4 g, and we want the other mass. So what this is an Atwood machine. On an Atwood machine, we have two masses, A and B. We're going to assume that B goes down and A goes up. So this will be our Y's. They have to follow the rope. If A is going up, B's got to go down. If A is dropping, B's got to go up. Then we only have the following equations. We'll call this AY, MB, AY. If we look at the free body diagram, everything has a weight. So for A, we have MAG, and then we have a tension in the rope up. For B, we have a tension in the rope up. We have MBG. However, we need to choose Y to be along the rope the way that they're traveling. So for A, tension is positive, MAG is negative. For B, I'm sorry, this should have been MBG is positive and the tension is negative. If I add these two things together, I get MA plus MB, AY is equal to MBG minus MAG. However, what we're trying to find is MB. So what I want to actually do is move this over, and what I get is MB A minus G is equal to the negative tension. All I did there was I moved over that. Then MA A plus G is equal to the tension. So if you notice, MAA, move that over. So I get that the following is true. How do I want to do this? What I want to do is something we've never really done before. I'm going to put a negative sign. I'm going to multiply through by a negative sign here. So I get G minus A now. This would be MBA minus G is minus G, but if you multiply both sides by a minus sign, then divide through by this. And what I get is I get MA over MB, A plus G over A, or G minus A is equal to 1. So you're just dividing both sides of that equation. If I multiply the reciprocal of this, what I get is G minus A over A plus G. And so I'm just doing this a fast way so that I can do the quick solution. However, what you could do is you could solve, you could actually plug this in this way. So MA A plus G is equal to T, which is equal to MB G minus A, since those two things are equal, and then you will get the same thing. However you want to do that algebra, but we're trying to find MA. So MA is equal to G minus A over G plus A times MB, which is a little weird for a Atwood machine. We usually don't know A. Now, we're assuming that one of these blocks has a mass of 1.5 and is accelerating downward at 3/4. So we're assuming that MB is 1.5 and that A is 3/4 G, or 3/4 times 9.8. If I put those numbers in, I get 9.8 minus 3/4 9.8 over 9.8 plus 3/4 9.8 is equal to times MB, which is 1.5. And that'll give me MA. You could actually do this a faster way by pulling G out of it, but I'm not going to. 9.8 minus 9.8 times 0.75 divided by 9.8 plus 9.8 times 0.75 times 1.5, and I get 2.214 0.214 kilograms, which they're calling 0.21 kilograms. So normally you would know that for an Atwood machine, A is MB minus MA over MB plus MA times G. That's for if B is falling for an Atwood machine. But in this case, we need to solve this for MA, which is a little bit of algebraic work. If you do it correctly, you get this answer and then plugging stuff in. The other weird thing is that they give you the acceleration as 3/4 G, and that just means multiplied by 3/4 by 9.8. So alrighty. There was nothing else. All right. Now I talked a little bit about this one in class. We have a person who's firing a crossbow, and they're going to fire it, and we're going to figure out what the force is. So they're standing, they're like Daryl on Walking Dead, they're firing their crossbow. And whatever force this thing has, because he's standing on ice, there's going to be a third law pair, there's going to be a force on him the other way. So the first thing we need to remember is our constant acceleration equations. Particularly, I believe this one, but I might need a different one. So we're told that he's standing, the mass is 75 kilograms for the person. At rest, he shoots a bolt with a mass of 0.450 kilograms. 450 grams is 0.45 kilograms. When released, the bolt reaches a speed of 110 meters per second in 0.25 seconds. And that was 110. B final is 110 meters per second. Time is 0.25, and B initial was 0. So we don't have X, and the only equation that doesn't have X is B final is equal to B initial plus AT. And this goes away. So we can find the acceleration, and then we can find the force, because it's actually the force that's a third law pair. This is the force of the crossbow, this is the force on the man, and whatever force is on him on the crossbow is equal to the force on the man, because they're a third law pair and he's on ice. There's nothing to absorb that force, if you will. So let's find our force. Our force will be the mass of the crossbow bolt times A, but A from this, A is equal to B final divided by T, which is 110 divided by 0.25, or a quarter. So this is 440 meters per second. This is 0.450 times 440. 0.450 times 440, which is 198 newtons. So our force on our man is 198 newtons. What is the force of the bolt on the crossbow that the crossbow man is holding? Now, the force on the crossbow due to the bolt, which is what force of the bolt on the crossbow. So as the bolt fires, it actually pushes back. You can think about this like in the movies when you see someone shoot like a rifle and it kicks back into their shoulder. When you fire a crossbow, the crossbow bolt basically kicks back into the crossbow. You get a little bit of a kick. That is the force that we just found. It's negative because they're actually asking for the force of the crossbow bolt on the crossbow, not this was the force on the crossbow bolt due to the crossbow. They want the force on the crossbow due to the crossbow bolt. So it's negative. What is the crossbowman's recoil velocity? Okay, so we need to find the acceleration on the man, which is the force on the man over his mass. That is 198 over 75. So the acceleration on him, and it's negative in the negative direction, it's 2.64 meters per second. The recoil velocity we find the same way. So V final, and remember that A is actually technically in the negative direction because it's the force acting on him. V final is AT, which is 2.64 times 0.25. And that is 2.64 times 0.25, 0.66 meters per second. So we basically just undid everything we just did. But it's negative because he's going backwards. So don't put the negative sign. Hopefully that makes sense to you. This question is all about third law pairs and understanding that for every action, there's an equal and opposite reaction. So when the crossbow's bolt is fired, there's that equal force on the crossbow, which makes the man go backwards with that force. But to determine his velocity, we need to find the acceleration. The acceleration on the crossbow bolt is different than on the man because they have different masses, which is actually Newton's second law. So I hope that's actually a fun problem for you. I like that problem a lot, actually. Okay, so this is a frictionless pulley, and we have two masses, one big and one small. And then we're going to try and find the tension in the string between them. So let's get just an expression for this. This is big M. This is little m. If I draw a free body diagram, big M has a normal force and big mg and a tension. There's no friction in the problem. And I'm going to draw X that way, and I'm going to draw Y that way, because once little m starts to drop, it's going to pull m to the right. Now for little m, the only thing that you have to be careful of on this problem is A has to go down, or X has to go down. This X and this X are the same. The acceleration along the rope has to be the same because we have massless, stretchless ropes. So when we write these, this is big M, AY is N minus big MG, which is 0 because it can't leave the surface, but we don't really care about that. We do care about, however, big MG, I'm sorry, not big MG, big M AX is equal to T. And little m AX is equal to mg minus T. That's just Newton's equations from these two free body diagrams. If we add these together, we get big M plus little m AX, T minus T plus mg. That's little mg. So our AX is mg over big M plus little m. So little m G plus big N, or over big M plus little m. They want you to do that in symbol, but they want the tension. Now the tension is here. So what this would be is big M would be the tension. So if I multiply big M there, I also have to multiply it here. The tension is big M times AX, but AX was little mg over big M plus little mg. So just multiply both sides by big mg, and we get big mg, little mg, big M, little mg over little m plus big mg, which is what we got. Now, So this part B is the same problem, but we're going to go back to, remember that our A was little mg over big M plus M, little m. And this problem says a 4K block is on the horizontal by a massless string, and A is 1.2 meters per second squared. Big M was, for me, yours may be different, 4.0. And we want to find little m. Okay, so if we back this up for a minute, we had that little ma was t, and big ma was, sorry, I had that backwards. Big MA was T and little MA was T minus MG. So we want to find little m. If we move this over, we get MA plus G is equal to T, or M is equal to T divided by A plus G. But remember, our T is big MA. So this is 4.0 times 1.2, which is 4.8 newtons. A is 1.2, G is obviously 9.8. So 4.8 over 1.2. Can't write tonight. 1.2 plus 9.8, which I get 4.8 divided by 11 is 0.44 kilograms. Hopefully I did that right. No. What? What did they do here? What did I do wrong here? Did I read it wrong? A 4 kilogram block on a horizontal frictionless surface connected by a massless to a hanging mass. For what value of the hanging mass does the block accelerate at 1.2? So, oh, okay. So this is what they got was big M. Big M A is equal to little m G minus A. Did I, going too fast, rewrite that wrong? So let me go back to this. I don't care about these, but normal mg, and I'm going to call this m1 like they did. Tension. Tension, and this is our unknown mass. This is mass 1. So what I get is I get m1a is equal to T, and m unknown m a is equal to T. I think that's what I did wrong. Mg minus T. We want to find this, so I get that. Yeah, that got to be what I did wrong. Move the T over. T is equal to M question mark G minus A. I think that is what I did wrong. So M1A is equal to M question mark G minus A, or M question mark is M1A over G minus A. And they told us that M1 was 4.0 and A was 1.2. So I get 4.8 divided by 9.8 minus 1.2. I messed up a minus sign. Sorry, guys. Which is 4.8 divided by 8.6, which is about 5.6 kilograms or 560 grams, which is what they got. So sorry. You got to be careful. Actually draw the free body diagrams. There's a lesson there. Instead of doing them in your head like I did. Trying to cut corners. It's been a long day. Now this one should look familiar to you because we've done it twice already, and we're doing it again. We have 3 blocks, and one of these blocks, there's kinetic friction in between the table surface. The other 2 are just hanging, so they don't matter. We want to find the acceleration of the 2.0 kilogram block. And for those of you who have missed it somehow, if this is, I'm going to call this one A, I'm going to call this one B, and I'm going to call this one C. We're going to assume that it's going to go down this way because C is actually 3 kilograms and B and A were 2 and 1. I thought so, but I wanted to be sure that I didn't mess that up. And mu is 0.35. It is 0.35. Now, if we do a free body diagram for each one of these, there's a tension on A to B. I'm going to call this rope 1 and I'm going to call this rope 2. So this is tension 1. This is MAG, and we're going to go up. So this will be our X along the rope. For C, there's a tension 2, and there's an MCG, and we're going to go down because we're assuming it's going to fall down. We're calling these X instead of Y because along the rope, I'm going to call X. For B, we have NB, the normal force of B, MBG, and then we have T2, the rope going to C. We have T1, the rope going to A, and we have a force of friction, mu K NB, which is due to, if it's going that way, the force of friction has to work in the opposite direction. And the force of friction is mu K NB. The book has a minus sign because it opposes the direction of travel. Now, the Y direction for MB is NB minus MBG, and that's equal to 0 because we assume that the B can't leave the surface, and that tells us that NB is NBG. We already know that, but fine. Let's do all of our X's. MAAX is T1 minus M1G. And MCAX is the opposite of that, MCG minus T2. So MCG minus T2. And then for MB, we get T2 minus T1 minus mu K MBG. So we have T2 minus T1. This one I should have said. T2 minus T1 minus mu K NB, but we know NB is MBG. So now if we add everything up, all the T's are going to go away, but we want to know what is the acceleration of the 2 kilogram block. So we want AX. So this becomes MA plus MB plus MC AX. T1 goes away, T2 goes away. And I get, what do they call this? I get MCG minus MAG minus mu K MBG. And if I divide both sides by all of that stuff, what I get is I get the following: MC minus MA minus mu K MB all times G over MA plus MB plus MC. Remember, this was 1, 2, and 3, and this was 0.35. 0.35. This one was 2, this was 1, and this was 3. And this was 1, 2, and 3, so the bottom is 6. What I get is I get 3 minus 1, which is 2, minus 0.35 times 2, divided by 6, all times 9.8, and I get 2.213. Sorry, 2.123. Don't round that yet. Maybe even leave another digit. But 2.12 is our, or 2.1 for the correct sig figs because they only gave us 2 sig figs for friction and the mass there. So 0.21, I'm sorry, 2.1 is the correct acceleration. However, we're going to need it still. Oh no, we don't. Okay. Sorry. We've done the same problem in different ways in the worksheet and in the quiz, and I'll talk to you about that soon, tomorrow. All right, so our final one, our final one. And this problem's actually hard. We have a physics book that's connected by a rope to a coffee cup, and it's going up, and then it's going to stop. So it's pushed up with some initial speed, and it's going to stop. And then what we want to know is, will it come back down? So how far up does it slide? So the first thing we have to find is, what is the acceleration of the book up the ramp? Let's draw this the following way. It's like this guy and then this guy, and we're going to be going up the ramp. So this is our cup and this is our book. Our cup is T, m mass of the cup G, and we're going to be going upward. This is sliding upward. Now, the book has, remember, this is on an incline, so we need to turn it. So it's like that. And so what we get is we get n mg cos theta of the book, and down was mbg sine. Okay, so that was the normal inclined plane. But we also have friction. So we have this force of static friction for now, not static, kinetic. And that force of kinetic friction, now this is going to be my x and this is going to be my y. For the y, for the book, n minus mbg cos theta is 0. So the normal force on the incline is mbg cos theta. My friction force of kinetic friction is mu n, or mu mbg cos. Now I need to figure out the acceleration because I know that it has some initial velocity. It's going to go up some distance. This is x initial is 0. It's going to have some x final, and v final will be 0. So we need to find a so that we can determine what x final is. Now, looking at these two things, I get m of the cup A is T minus m of the cup G, and m of the book A is negative mbg sine theta minus force of friction mu m book G. Now adding those two things together, oh, and I'm sorry, there's also a tension that I almost forgot. I caught it because it's got to go away. So what we see is we see that we have the following. M of the cup A was T minus M of the cup G. And M of the book A was minus T minus M book G sine minus mu K M B G cos. Now, adding these things together, the T's will go away, and what we get is that MC plus MB A is negative MCG minus MBG sine minus mu K MBG cos. Divide both sides by MC plus MB, and we get the acceleration. Once we have that, we know that x initial is 0, x final is what we want. V initial was given, for me it was 3.5. And V final will be 0. We want to know how far it slid. So we need to find A. We don't know T, and we don't need T. So to find that, we're going to use B final squared minus B initial squared is 2A X final minus X initial. But we got to find A first. Now the cup is 55 grams. MC is 0.550 kilograms, everything in SI. Gravity is obviously 9.8. The book, mass B, is 1.5 kilograms. And mu K is 0.2. It is 0.2. So this is 0.550 times 9.8. This is 1.5, 9.8. What was the angle? 20 degrees. This is 20, 0.2, 1.5, 9.8, and 20, just so that I don't forget things when I plug them in. Notice that they're all negative. 0.550 times 9.8 plus 1.5 times 9.8 times sine of 20 plus 0.2 times 1.5 times 9.8 times cos 20. And I get 13.18 at the top divided by the two masses, 0.55, so 2.050. I get 6.4295. This is 2.050. So I get 6.4295 meters per second squared. That's my A. I'm trying to find X final. This A is actually negative, which means that X final is B initial squared over 2A, which is 3.5 squared divided by 2 times 6.4295. The negative sign went away with this negative sign. So I get 3.5 times 3.5 divided by 2 times my answer. I get 0.953 meters, so about 95 centimeters. So we have we only have 2 sig figs here, so use 2 sig figs in your answer. So 0.95 meters or 95 centimeters. Then we want to know, will it slide back down? And when it slides back down, the thing that we need to look at is we're going to, instead of having this friction is going to become static friction. So static friction. Further, all of our signs are going to flip. Okay, so we're going to flip this to down, and we're going to flip this one to the following way. And then what we need to figure out is if the net force down is greater than the force of static friction. So let's pretend like there's no static friction here. The net force down on this one, I'm going to just get rid of all my signs for a minute. So for this guy, it is, while it's trying to slide back down, mcg minus t. And this would be t plus mbg minus static friction. But for now, hold off on this. I want to know if this stuff is going to be greater than this. Basically, if I add up all the forces and I get some negative number, then it's not going to slide down. Or if I get 0, it's not going to slide down. However, if this is all greater than this, it will. So sum up the forces, and basically what I'm saying is MCA plus MBA needs to be equal to or less than 0, meaning it can be negative. And that side of the equation is MCG minus T plus T, the T's go away. So MCG plus MBG sine theta minus mu S MBG cos theta. This is the force of static friction, and this is the weight of the book, and this is the weight of the cup. So let's add those things up. Remember this with 0.550 and this with 1.5 and this 20. So I get 0.550 times 9.8 plus 1.5 times 9.8 times sine of 20. This whole thing is 10.4176, these two forces. This one, mu s was 0.5. So this one's, stop it, 0.5, 1.5, 9.8, and cosine of 20. 0.5 times 1.5 times 9.8 times cosine of 20 is 6.906, assuming I did that right. That means that the static friction is not enough to stop it from sliding back down. It's going to slide back down in our case. I don't know if some of you may end up with ones that stay, but what you're looking for is the sum of the forces needs to be 0 or less. That means that the static friction wins over the weight trying to pull it back down the ramp that the book is on. Hopefully that makes sense. If not, we can talk about it tomorrow. For those of you that are here, or those of you that have watched this video so far, what I mentioned in the announcement, I also wanted to tell you that worksheet 3 solution, worksheet 4 solution, problems, chapter 7 solution are all there. Quiz 4 solution is there. And then I posted, for now, there's a practice exam 2 PDF. As always, there will be far less questions on here. And we'll go over this next week. But on Sunday, I will post the solutions. So this is a practice exam. Actual test question will be 3 to 4 short and 2 to 3 long. So there's a few short answer questions that you can do pretty fast. And then there are 2 or 3 longer ones that you need to do. But we'll go over those, the answers next week, and the answers won't show up until Sunday so that you guys can try without being tempted, but to look at the answers, you can try and do the test. I would try and do the test without looking at the answers first, try to solve them, and then see if you're right after you think that you've solved them correctly. But otherwise, hopefully this homework wasn't too bad. I know the homework that I just assigned really isn't too bad, but I'll probably do that one Sunday for you or Monday. Our test is Friday, so a week from tomorrow. So anyway, unless you guys have questions, I'm going to end the meeting. Itzel, Lyra, I don't know who that is. Joseph, are you guys okay? And I know.
Yeah, I'm fine. I think that would, I'm good with the questions.
Okay. Thanks, Lyra. I'm going to end this, guys. I'll see you tomorrow morning.
All right, then. Good night. Thank
night.
you.
Bye.
Bye, guys.
Thank you.